classic problem. You are walking away from a light source and your shadow is moving. How fast does the shadow move? This is a classic related rate problem. Because more than one rate is being acted upon each other. For instance, person has a rate of speed and the shadow has a rate of change. There are 4 steps to solving every related rate problem. 1. Draw a picture. 2. Find an equation. 3rd, differentiate. 4th, solve the given situation. Here's a person walking away from a light source. Here is the light. And here is the shadow will be formed later on. So what I've done is connected the light source to the tip of the shadow as the person is moving. So now we need to find an equation to represent the situation, and we will use, I can see similar triangles are here. You've got a small triangle here, you got a big triangle here, and it just so happens I find out that the lamppost is 3 meters tall, and the person is 2 meters tall. Now 2 variables that appear in this problem. One is the distance between the lamppost and the person walking. I'll call that x. Then the distance between the person and the tip of the shadow, I'll call that s, for shadow. X stood for unknown variable over here on the left. Let me make a basic sketch of what we're looking at here in geometry terms. We've got 3, 2, x, and s. And both of these triangles will be considered a right triangle. Smaller right triangle is also evident. Let me create my equation now. I know I have the bottom part of the big triangle, x plus s, over the left side of the big triangle has to be equal to the bottom part of the small triangle over the left part of the small triangle. Since my position and the shadow both are based as a distance based on time, let me rewrite this equation in calculus talk. X of t plus s of t divided by 3 equals s at some time, that's the shadow length at some time, over 2. Okay, let's do the derivative of both sides. The derivative of the left side, that's just x plus s all divided by 3, so that's just 1/3 times the derivative of each component. So I'll call it x prime t plus s prime of t have to be the 1/2 times the s prime of t. That turns into nothing more than 1/3 x prime of t plus 1/3 s prime of t equals to 1/2 s prime of t. And we can combine like terms. So I will subtract 1/3 s prime from both sides. That will give me 1/3 x prime of t equals to 1/2 s prime of t minus the 1/3 s prime of t. Okay, 1/3 x prime of t equals to 3 minus 2 is 1 over 6th s prime of t. Now we're going to isolate either x prime of t or s prime of t and solve one for the other. Solving this for s prime of t by multiplying both sides by 6, I get 2x prime of t equals to s prime of t, which implies the change of the shadow is 2 times the change of the person's position from the flagpole, the light source, not flagpole, the light post. What's fascinating about this solution is it doesn't matter where the person starts from walking from the light source. It doesn't matter because we're not even talking about where he is, the x value. This is x prime. That's the speed of the person walking. And this is the speed of the shadow moving. So irrelevant of where we start out at, this is going to be a general solution for all the cases of the same problem, is that the shadow will always be moving at twice the speed of the tip of the shadow will always be twice the speed of the person walking. And I find that fascinating. One other point we need to make is recall that the lamppost was 3 meters tall and that the height of the person was 2 meters tall. So this is the case for those particular constants always being true. It's going to change if either of those numbers change in a future problem.